Hi everyone. In today's class, we're going to look at the final gas law called the ideal gas law. The ideal gas law basically combines all four factors that affects a particular gas into one single formula. So the formula that you see in front of you right now, PV equals nRT, that is the ideal gas law. Okay, sometimes we call it PIVNRT for short, but it involves pressure, volume, moles, and temperature. So we do have a couple of conditions that's located in this box here. So just like your other gas laws, these conditions basically apply to the units that pressure, volume, moles, and temperature are measured in. So for pressure, P, you have to use the measurement in units of kilopascals. For volume, it has to be in liters. For moles, it's just in moles. And then for temperature, the unit has to be in degrees Kelvin. Okay, so any pressure that we give you, you gotta convert to moles. Kilopascals. If I give you milliliters, you have to convert to liters. If it's given to you in grams, you'll need to convert to moles. And if you're given temperature in Celsius, you'll have to convert to kelvins. Now, you'll notice something very odd about the formula. We don't have P1s, T1s, P2s, T2s, etc. So there's no final or initial volumes or pressures or temperatures or even moles. Okay, this particular gas law operates in the current moment. Okay, not a before or after, and because of that, it makes it very useful. Okay, we have a certain amount of freedom now to use this gas law in more or less real time, so we don't have to have a beginning and an end. So the other problem though is, in order for the gas law to work, there needs to be a constant. So just like in Boyle's law, temperature and moles have to be constant, okay, in order for you to test pressure and volume, right? And in Charles' law, pressure and moles have to be constant, okay? So it's not that much different from the ideal gas law. It's just that we derive our constants through experiment. So the R, okay, the variable R, is called the gas law constant. And the value that we're going to use for this particular gas law is 8.31, and the unit is liters times kilopascal divided by moles times Kelvin. Okay, but it's the actual number here that's a little bit more important. So because this constant has the following units, okay, that's why our pressure has to be in kilopascals, our volume has to be in liters, our moles has to be in mole, and our temperature has to be in Kelvin. Otherwise, this value would not work. Now, if you do look online for gas law constants, there'll be a whole list of them, okay, and they differ because the units differ. So that's why we're making it simple for you guys. We're just going to stick to this one variation of your gas law constant, and it's going to be 8.31. Okay. Now, the gas law itself is fairly useful in everyday situations, but it's not as accurate under extreme conditions. So we'll never encounter these extreme conditions. Okay, not at least it's not likely. So if we wanted to take the pressure, okay, of a gas that is on the surface of the sun, where it's very, very hot, okay, that would be an extreme condition. If we wanted to look at the volume, okay, deep in the ocean, underneath a lot of pressure, that would also be an extreme condition. Okay, so most everyday conditions are fine with our ideal gas law. It's just those particular kind of conditions where your pressure, volume, temperature are in the extreme. All right, so I want to go through two sample questions with you guys. in terms of using this gas law, it's the easiest one out of the 5. Now, recognizing when to use it, okay? Most of the time when you want to uh, solve some kind of variable, whether it's pressure, volume, temperature, etc., okay, there's a list of, variables for you to figure out. Well, the list is a little bit shorter here, okay? But the ideal gas law does allow us to do similar things that our other gas laws does as well. So in this question, we have at STP, okay, so remember that's standard temperature and pressure. They're asking for what volume would 15 grams of helium occupy. Well, helium is a noble gas, okay, and they're giving us a mass, okay. So I always want you to figure out the variables. Okay, so here are the 4 variables. Do we have pressure? Well, yes, it's at STP, so it's standard pressure, which is 101.3 kPa. Do we have volume? No. They want you to figure out what volume is. Okay. Now, N. Do we have moles? Okay. No, we actually don't have moles. However, we do have the means to find moles. So in our case here, it's 15 grams of helium that we have to convert to moles. So you'll need to use your periodic table. Okay. Look for helium. Helium's over here on the right-hand side. It has a molar mass of 4. So we basically just convert by dividing by the molar mass of helium. So 15 grams divided by 4 gives us 3.75 moles of helium. Okay. And then as for temperature, well, you're at STP. Standard temperature is 0 degrees Celsius, so we have to convert that to Kelvin. So we add 273 to it, and that'll give us 273 kelvins. Okay. So we have pretty much everything that we need. R is the constant, so we already know that value. That's going to be 8.31 liters kilopascal and moles Kelvin. Okay, so all we do, we'll set up the formula. Pivot PV equals nRT. We want to solve for V, so we divide both sides by P. The P's cancel out, you're left with volume. And now we just substitute our values in. So 3.75 moles of helium. Now I am going to put in the units this time for the gas law, because I want to show you how they cancel out. And then we have 273 as our temperature, all over 101.3 kPa. Alright, so moles and kelvins. Okay, so moles and Kelvin will cancel out because they're on the denominator of our gas law unit. Okay, and then kPa cancels with this kPa because again, top, bottom, numerator, denominator, they both cancel each other out. So you're basically left with volume in liters, because that's the only unit that isn't cancelled out. So if you multiply everything on the top and divide everything on the bottom, it will come out to 83.98 liters. So that's our volume. That's how much 15 grams of helium would occupy if the gas was at STP. Okay, so if you wanted to figure out pressure or temperature or moles, okay, you just have to manipulate the formula once and then insert everything in. So it is really as simplistic as that. Okay, so that's the first question. The second sample question is a little bit more difficult because we're asked to do more. Okay, and we can use the ideal gas law to find out more than just what variables are given. So for example, we can actually use gas laws to find out molar mass and perhaps the identity of an unknown gas. So in this question here, you are given 70.05 grams of a diatomic gas. Okay, so diatomic again means that these atoms don't like to be by themselves. They're always paired up with another atom of the same kind. So something like oxygen. It wouldn't just be a single oxygen, it would be O2. Okay, so as a gas, it always occurs as O2. So you're given this diatomic gas. It occupies a volume of 56 liters at 0 degrees Celsius at normal atmospheric pressure. And they're wondering what the molar mass is of this gas. And then, after that, figure out the identity of this diatomic gas. So again, write out everything that you have. Okay. Do you have pressure? Yes, it is normal atmospheric pressure. So we just make it a little bit convenient for ourselves in these two sample questions by having them being pretty much at STP. The volume is at 56. Okay. The number of moles we'll get back to, but temperature is the next easiest one at 0 degrees. So you add on 273 because we can never use Celsius in degrees. And that will be 273 Kelvin. Okay. N. Well, you have 70.05 grams. Okay. Without actually knowing what the diatomic gas is, I cannot figure out what kind of molar mass. So I cannot convert this mass into moles. So that means I need to figure out what moles is. Okay, I have everything else. Okay, because remember, R is constant. It's 8.31. So as long as my pressure is in kilopascals, my volume is in liters, and my temperature is in Kelvin, I can use this 8.31 to find moles. So again, PV equals nRT, pivnert. I'm trying to find N, so I divide both sides by RT. RT cancels out, and basically N is equal to pressure, so 101.3 times 56 liters over R, which is 8.31, times T, which is 273. Okay, so once I figure out this calculation here, N is going to be equal to 2.5 moles. Okay, that's the moles that I've calculated for this gas. But the first question was, what is the molar mass? Okay, well, molar mass is always grams per mole as the unit, right? So grams is basically your mass divided by moles. And I have that. I have 70.05 grams divided by the moles I just calculated, which is 2.5 moles. And that will give you 28.02 grams per mole. This is my molar mass. Okay. Now, we figured out the molar mass part, but what about the identity of the diatomic gas? Well, here's the thing. If you looked for 28.02 grams per mole on the periodic table. The closest value that you might get is silicon, which is at 28.09. Okay, and certainly silicon could be heated to a gas, but it's not a diatomic gas. Your diatomic gases start with hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are the diatomic 7. So to figure out which one you actually have, you have to take this value and divide by 2. Okay, you have to separate or take into consideration the diatomic aspect of this gas. And when you do that, it becomes 14.01 grams per mole. And that is the value for nitrogen. So this is the molar mass of nitrogen gas. Okay, because a single nitrogen, its molar mass is 14.01. So this type of question is pretty common. Okay, you don't actually need to calculate or figure out the identity of every single gas that we give you. Okay, for the most part, if we ask you for the molar mass, okay, that's one separate question. And if we decide to ask you the identity of this gas, okay, look on your periodic table to see if there is a substance that matches the molar mass. Now, most of the time, if it is diatomic, I'll let you know that it's diatomic, okay, just so that you can divide by 2 to find out the actual identity. But if I don't say it's diatomic, you don't have to assume that every gas is diatomic. Okay, just look on the periodic table to see if you have an element that matches up with the molar mass. All right, that's all I have for today. Hope to see you guys soon. Take care.